Hey, everybody. Happy Wednesday still, or whatever day you happen to be watching this. We're just gonna let it ride and go ahead and go into second lecture for our first unit. So I'm going to fire that up. And then, all right, so today we're going to jump into our second lecture, which is going to be on digital image formats. So in the last lecture, we talked a lot about what a digital image is and what a pixel is and how we kind of figure out what type of digital image it is based off of what information is in the pixel. So now kind of for the second lecture, we're going to be talking about those formats. So kind of what formats are there for digital images and what are the pixels that correspond to it. And then sort of how we represent images in code, and then how we go between formats. So we'll talk a little bit, a little introduction to this idea of coordinate transforms as kind of the core concept of computer vision. So last time we talked about basically just what is a digital image. And we sort of figured out and talked through how it's just a multiple dimension function where there is some function that determines what the pixel looks like to the computer. And we saw, for a 2D image, that's going to be f of xy, where xy is just the indices of the array, which in turn is just where in the display the pixel is located. Or beyond just a sort of 2D image, we also talked about this idea that a digital image is just an array of arrays. And, in a 2D binary image we saw last time, that value is a 1 or a 0. Or if we had a grayscale image, that would be some value between 0 and 1. Or for a 2D color image, each pixel is an array containing the red, green, and blue values. And then for 3D images, it's the same thing. It's just now the array has a third dimension, that's your Z value, and then inside each pixel is still your X and Y values or your RGB values. And so when we talked about it, we said, last time we have our two-dimensional array or three-dimensional for 3D images, or we'll see much, much higher sort of bigger arrays representing pixels. But at the end of the day, we have sort of established that a digital image is some n by n array of discrete values, and each entry at each n by n indices of the array is a pixel, and each pixel is a set of discrete values. And so we saw last time, we could just do a simple right, we have our identity matrix, and that turns into, oops. All right, and so then we have our binary image. So the idea is, can M or N be 1? So we can't have a single pixel digital image, right? M or N has to be some value greater than 1, but you can still have an image that has 1 indices as 1, because that's essentially what each line of a display in a CRT is, you know, a 1 by resolution sort of image that is rendered one line at a time in our CRT TVs. And so you could have, you know, dry erase markers. Okay, so we can have kind of our one-dimensional where we just have M is 1 and N is 2. And so 1, 0, we get a black and a white pixel. So you can have a one dimension can be 1 in a digital image, but they can't both because, like I said, 1 pixel value isn't really an image, it's just a value, right? But once we start increasing the size of the array, we can start treating it like an image. So then, you know, we talked about, now we're going to talk more about what actually is a pixel. So, you know, we know a pixel is an array, and it's an array of discrete values. We know that pixel is located at its array indices on the display. So your X and Y is your I and J, or M and N, or however you want to sort of think about it, but where it is in the array is where it is in the image. And so each sort of array value is each pixel is one of the small squares that make up an image on a computer screen. So we talked about that last time with, you know, sort of Duck Hunt versus Halo. In the physical world, a pixel is just literally a place within the display or within the image that turns a color or turns an intensity, or is black or is white, right? The pixel physically is sort of the base discrete place within an image, right? It's kind of the smallest part of it. It is sort of contained within the broader image, and then there is physically a thing on the screen that then renders that color. And so we also said, and are talking through a little more now, that the information inside of the pixel determines the format of the image. So when we think about a grayscale image, that's going to be an image of pixel values between 0 and 1, with 1 being fully black and 0 being fully white. So if a pixel is some value between 0 and 1, then kind of the computer and us as the person know that we're working on, you know, some variation of grayscale image. Or if I have RGB values in my pixel, then I know I'm looking at a color image, and I can, you know, the computer thinks of it in terms of a color image, and I let it know that. So we kind of have this idea of, you know, besides binary, besides grayscale, and besides color, what are other values we can put inside sort of this construct that is a digital image, right? What are the arrays that represent the pixels that we can stick into our bigger array that represents a screen or an image resolution? So I've got this. I won't play it here, but if you want to go watch this, every time I think my 20-year-old pop culture references won't translate or whatever, I get proven wrong. But this is from the Battlestar Galactica reboot. And it's just a video of one of the evil robots complaining about why the human that built it only let it see visible light, right? You know, it's not constrained by the biology of the human eye. So there was, you know, no reason the robot couldn't see gamma rays or radio waves. And that's kind of part of the gist of what we're talking about these first few lectures. For computer vision is that, as I've said a few times, there's no reason to bind an image in a computer for computer vision to this idea of a color image or a black and white image of visible light. Because a computer isn't human, and you can do computer vision on things like, gamma rays or radio waves. You can sort of break out the energy inside these bands and still create an image. It's just one that only makes sense to a machine. So along those lines, representing sort of a general digital image is kind of like we've talked about, this idea that we've got pixels and a location. And that's what our image is. So it's an array that's an image, and it's an array that's pixel values. The array that's the image, sort of the big array containing the pixels, cannot be just a value. It has to be some sort of array, even if one of the dimensions is 1. But also, you can put basically any amount of stuff into the pixel that you want, and then the computer will think about that and put it within the digital image. So the size of a pixel is pretty much arbitrary, and the information you put inside the pixel is also pretty much arbitrary. And there are just sort of a subset of pixel values that computers can look at and humans can look at, and we can do sort of these digital image processing tasks on. Like I mentioned last lecture that we might get to towards the end of the class, some of the stuff we do in computer vision, we can do in other fields because computer vision is built to just essentially look at an array of arrays and then think about it and give you back some sort of result or some sort of information you want. But you're really not limited to that. And when I was in graduate school, some guys were doing like stock market forecasting using some image processing type of techniques because it was just, a stock's price in a day. So you had a bunch of stuff that was a price in a day, and so each pixel had 2 numbers in it, and then you could throw some weird computer vision stuff at it and see what happened, and it was a fascinating project. I don't really know if it went anywhere because I graduated and kind of left from its beginning, but all that to say, a pixel can be abstracted to any sort of discrete numerical data. So we can think about our grayscale image that's all between 0 and 1, or we can think about a thermal map. So you can look at, kind of the temperature across something like a tire or a rod in a system or a pipe. And that is, you can turn that into a heat map that is between, some lower bound of temperature and some higher bound of temperature that you've normalized, and it turns into a binary image that looks a lot like a grayscale image, but we just so happen to have colors associated with a temperature instead of, colors associated with a shade of gray. But along those lines, this is one of the things we mentioned last class, and it merits a second mention, is the idea that a digital image looks a lot like a time series because it's changing with X and Y values. The difference is that a time series is continuous. So information between point N and point N plus 1 in a time series exists. There's some sort of continuous function we can fit that will give us values between, one point in time and the next point in time. So a time series is a continuous set of data, right? And so we can't do any of the signal processing we like to do on time series to images because the value at each pixel is discrete. So there's no function that will tell you what the area between those two pixels should look like, right? There's pixel 1 and pixel 2 in an image, and there's, you know, 0.1 and 0.2 in a time series. So that's kind of the distinction, and that just sort of helps highlight this idea that, you know, pixels are discrete. Pixels only have their information in them, and pixels don't really talk to each other when they are being rendered. So every pixel is kind of in business for itself and gets put somewhere in the display and given some value. A time series, everything sort of runs together continuously, and point A and point B do have information that exists between them that we can pull with some sort of function. So, and here's just sort of another instance of that where we've got kind of time and temperature. And so this would not be an image. We couldn't treat this as an image because it's, you know, this continuous function versus what we've seen about images. So to kind of move along and start heading in a doing CV direction, we're going to look at a few different image formats this semester. Obviously, we're going to be doing a lot with 2D color images because that's just what foundation topics work with. Two-dimensional IR and X-ray images are also really common. I know everyone at this point has heard about, you know, machine learning, and it's better at finding tumors and X-ray images and these types of things. So, you know, we'll talk about that a little bit. And then the idea of there are hyperspectral imagers, which are like, you know, the Cylon robot, wishes it could be, where you have broken all of light down into, you know, 1,000 or so kind of bands, and you can collect information across, you know, a much, much bigger spectrum of light than just visual light. And a lot of hyperspectral stuff is actually on satellites and is a huge part of forestry and agriculture now. Because with hyperspectral images, the type of computer vision you do can tell you what, you know, the soil is at a certain point, and what the soil moisture is, or kind of what vegetation is there, what crops are there. All those kinds of things can be pulled out of a hyperspectral image very well. And if you're just working with a 2D color image, there's really a very low ceiling on the information you can get out of that for most applications, but especially for any sort of kind of land usage application. But we'll talk about that a little more towards the end of class when we've got kind of some free time to explore topics. So, you know, we kind of go back, and here we are again with this idea of our 2D image formatting. We've got our RGB values for each pixel, and the more pixels we have, the prettier the image gets, or kind of the more continuous things start to look. And we can, you know, do lots of cool stuff. And also, it's a myth that sitting too close to a TV will hurt your eyesight. I think that's something my parents' generation just told kids because they thought we were annoying. All right, so if we look here, our image format is, you know, our pixel XY location equals some RGB color value, right? And so when we think about formatting a color image, we have our location of a pixel within an image, and the idea is how can I take the information in that pixel and turn it into something else, right? How can I go from a black and white image to a pink and white or a red and white image? You know, how do we sort of work with this idea of a 2D color image and the idea of color within pixels? So when I think about representing color within pixels, what we're talking about is our pixel is some RGB that's discrete, but in a way that makes sense to a compiler or a rendering image. And the way it makes sense to a compiler or a renderer is this idea of color banding. And the idea of color banding is we're essentially asking the question, how much green is green, right? How does the computer know how green to make the grass versus the dark green of the shadows around the bushes of the tree, versus the brown of the ground? This idea of, it makes sense to us, and we've seen it a lot. We're all, very familiar with this RGB value from digital images and so on and so on. The thing is a human eye, like I mentioned, sees things differently. But in order to tell the machine how much green is green, we have to do what is called color banding. And it's essentially, we want to break down the visible light into different parts of the spectrum. So the red part, the green part, the blue part. And then we count the intensity of, if you're thinking about a camera or a digital display, you're basically looking at the intensity of each of those three colors and then combining that intensity into one single color or hue that a person sees and says, oh, yeah, dope, that's green. So we have to figure out, like I said, how to tell the computer how much green is green. And we do it with this idea of color banding. And so RGB are each within sort of their color band. And for just a simple 2D RGB image, it's a 0 to 255. And so the way we kind of get at this, how we kind of got here, is it's a measure of intensity and saturation. So the higher the number in each color band, RGB, essentially the more intense that color is within the overall image. And the way to think of it, and this is one of those things that kind of goes back to where you started, if you think about a camera, when you open the shutter, essentially what a camera is doing is just counting the number of photons that hit the imaging plane, be that film in old cameras or like a charged couple device in a digital camera. It's essentially, you take a picture with a camera by opening the shutter, and then while the shutter is open, the camera counts essentially how many photons of each wavelength enter through the lens to the imaging plane. Or you can think about it like a human eye. When your eye is open and light goes into your eye, you have your imaging plane made out of squish and meat that is also essentially counting photons inside energy bands. So if we kind of set green as this section of the visible spectrum, when we open the shutter, what happens is all of the photons inside this sort of band of wavelengths get dumped into green. And so the camera counts however many pixels, however many photons hit within that color band to give back sort of the final green value between 0 and 255, wherever that is. And so with RGB images, you only have 3 bands of color. So the most basic example of color banding would be, you could have a pixel that's only red, or a pixel that's only green, or a pixel that's only blue. And so that would just be 255 and some zeros, which would give us this image, essentially, where I've just set, the color, one color, so red or blue in this image, the rest are kind of blends. But the idea is there's some value inside this color band that tells the machine how much green is green, when it renders the image, essentially. So if we go down, this is kind of that, and kind of talks through that a little more, which is the idea of, a pixel is some measurement of energy, in this case for a color image. And that amount of energy is broken down into color bands. And then the computer sort of sees a final image that is, for a camera, a number of photons in each color band. For a digital image, it's more about kind of the amount of green we're telling the compiler to display. But the compiler looks at it much the same way the person does, where, the more energy there is in a color band, the more that color is going to show through. But on kind of the other end of the spectrum, if we talk about IR images, infrared images also have 3 color bands. So band 1, band 2, band 3. So for visible light, we've got these 3 bands that give us the amount of red, green, and blue light, or amount of red, green, and blue photons, essentially. And then infrared images are also banded into a 3-dimensional array, where each band contains some set of wavelengths. So again, if you look at it, we're looking at an IR image, and we're counting the intensity of the light between each wavelength values in each band. So there's IRB, IRA, IRB, and IRC. And each one just has a discrete number of pixels in it. And that number of pixels in each band then tells the computer what the image should look like. And so here just kind of some example IR images. So on the left, this is the heat map we mentioned last time, where the values are between 0 and 1, where 0 is totally cool, like that upper left corner that's black. And yellow and then red are areas that are hotter. So you can see, in this sort of transmission station, a couple of parts are much hotter than the others. And you can kind of get that information and then do something with it based off this image. So that's kind of how we make a IR image visible to a person, is, the computer vision can do all of the work it needs to do here in these 3 IR bands. I can pass these 3 values to computer vision in the exact same way I can pass RGB values, or any sort of information inside an energy band. So this is, like I said, I'm going to say it a lot, the computer can work with this. A person cannot, right? A person cannot see this. So in order to make it something a person can look at, we sort of go through these steps to create our, heat map image or IR image that goes from, 0, which is totally cool, to 1, which is totally hot, which is this yellow. And so that's kind of the key takeaway here, is that the computer doesn't care what these energy bands are. It can be IR, it can be, like I said, hyperspectral that's got 1,000 energy bands. Doesn't matter to the machine. It only matters when a person wants to look at it. And so what happens with that is that now, kind of starting with the next lecture, we're going to be talking about converting image formats. Because the idea is, different computer vision tasks work better on different formats of images. So if I wanted to do edge detection, that is typically done with binary or grayscale images. But if I'm a person who's trying to segment that image and find something, I'm going to look at it as, an RGB image, and that's going to kind of make sense to my eyeball. Whereas the grayscale or binary image is what makes sense to an edge detection algorithm. And so next time we're going to talk about this in a lot more detail, with this idea of how do we go from, the IR energy bands to the visible light energy bands in a way that makes sense to a person, while at the same time, how do we do our computer vision task on something like IR bands that we cannot see? And one of the ways is to create a heat map like this and work on temperature values. But like I've said a bunch of times, there's no reason we have to do that to do computer vision. But anyway, that's what we're going to talk about next time, is just this idea that what's inside a pixel tells you what kind of image you're looking at, whether it's a color image, an IR image, a grayscale image, a hyperspectral image. Whatever information is in a pixel tells the machine what kind of image it is. And then the array that contains the pixels determines kind of the size and the resolution of that image. So we're going to talk about going forward how we change the values inside the pixels to look, air quotes, look better to different computer vision algorithms. And yeah, so that's what we're going to kind of go through, and we're going to see that sometimes we actually do that several times to complete a computer vision task, where we're kind of having to move back and forth in the pixel space to different coordinate systems, RGB, IR bands, whatever it is. We're going to have to be really smart about knowing how to change image formats, and when you do that and why we do that. And then I've just got, again, some additional stuff up on my courses you can go in and look at. There's some stuff, mostly links about how we use computer vision to find out things or do tasks that are not looking at color images. And then the Earth observation imaging, that's just a really cool paper about kind of going from RGB to hyperspectral, and going from, a helicopter to a drone to a satellite, and, what we can do with different image formats, and what we can do with color bands people can't see. So I recommend checking that out. I'm going to go ahead and stop sharing. So yeah, all right. That's lecture 2, digital image formats. Next time we're going to be talking a lot about coordinate transforms for pixels. So turning one pixel into another kind of pixel for one algorithm versus another algorithm. And then I think after that, there'll be some demos in Python we can go through. So again, any questions, comments, concerns, whatever you need, email me, DM me, and talk to you all later.